In the last lecture, we have derived the Black-Scholes model for European put option. The main attraction of the Black-Scholes model is that we can write the model in an explicit formula. In this lecture, we will derive the explicit formula for Black-Scholes model. First, we will establish the formula for put option, and then using the put call parity, we can also establish the formula for call option. Let us start with the Black-Scholes formula for put option. This can be written as a corollary to the theorem on Black-Scholes model. The statement says that the Black-Scholes price P naught can be written as P naught equal to K e power minus RT phi. Remember, phi is the standard normal distribution function evaluated at D minus, we will tell what it is, and minus S naught phi of minus D plus, where phi is the standard normal distribution function given by phi of x is equal to 1 by root 2 pi integral minus infinity to x e power minus x square by 2 ds. Let me write it as S square ds for all x in R. And what are these d minus and d plus? And d plus or minus is equal to log S naught, which is the initial price of the stock, divided by K, which is the strike price of the put option, plus R plus or minus sigma square by 2 into capital T, where R is the prevailing interest rate continuously compounded, and sigma square is the volatility, that is the variance, sigma into root T. T is the expiration date. Let us derive this formula. Recall that the Black-Scholes price is given by P naught is equal to E of e power minus R T PT, where PT is the payoff of the European put option. Therefore, this can be written as e power minus RT maximum of 0, k minus S naught e power x. And now I will take e to the power of minus RT out and write e of maximum of 0, k minus S naught e power x. Recall that x is normally distributed with mean r minus sigma square by 2 into t and variance sigma square capital T. Therefore, x can be written as r minus sigma square by 2 into capital T plus sigma root T into z, where z is standard normally distributed random variable. Now let us see when this maximum achieves and try to write this condition at which the maximum achieves in a more simple form. Look, the maximum is achieved when S naught e power x is less than k, and that is if and only if S naught into exponential of, I'm just substituting x by this expression, I'll get r minus sigma square by 2 into capital T plus sigma root T into z. And that should be less than k, right? And that is if and only if, just take S naught to the other side and take logarithm on both sides, we will get r minus sigma square by 2 into capital T plus sigma root T into z is less than log k by S naught, which I can write as minus log S naught by k, right? I'm just rewriting that. And then we can keep z on one side and take all the other terms on the other side to get z less than minus log S naught by K minus or minus sigma square by 2 into capital T divided by sigma root T. And remember, this is what we have denoted by minus D minus. In the statement, we have written this. D minus is log S naught by K plus R minus sigma square by 2. That is what is here. Log S naught by K plus, so I am taking minus outside. So R minus sigma square by 2 into T divided by sigma root T, which is also there here. So what we got is the maximum is achieved if and only if Z is less than minus D minus. That's what we can see. Therefore, exponential of maximum of 0 comma k minus s naught e power x can be written as k times e of the index set at st less than k. This is directly you can write minus e of st my less than k, right? This you can write directly, and you can now replace st less than k by z is less than minus d. Okay, so that we will do when we are computing these two terms. Let us take the first term. Let me call this as I1 and I2. Then I1 is equal to exponential of 1 st less than k, and that is equal to e of the index function on the set z less than d minus d minus. That's a pullback of that. And remember, this is the expectation for the random variable x. Therefore, you have p of minus d minus. So that is for the first term. And let us now compute the second term. We have I2 is equal to e of st, the index function at st less than k, and that can be written as e of s naught into e power x 1 st less than k, and that we can write e power x as we have already written x in this form, so you just substitute this expression here. Before that, you take s naught out and you have e of exponential of r minus sigma square by 2 into capital T plus sigma root T into Z, the standard normal distribution, times you have 1 this part, and instead of st less than k, I can write z less than minus d minus. Okay, because we have shown that both are equivalent, and therefore I can write this. Again, you can remove this e power rt out. That is anyway deterministic, therefore it can come out. E power rt and s naught, you have e of exponential of minus sigma square by 2 into capital T plus sigma root of capital T into Z 1 into Z less than minus D minus. And now you can apply the definition of expectation, and that gives me e power rt into s naught integral minus infinity to minus d minus, because you have this, and 1 by root 2 pi into, okay, so this expectation is actually defined like this. And now you use a change of variable. S is equal to xi minus sigma root t. If you put, we will get I2 is equal to e power rt into s naught integral minus infinity to minus d minus minus sigma root t 1 by root 2 pi, which can go out, e power minus s square by 2 ds. Okay, note that we have taken d plus is precisely, you can write it as d minus plus sigma root t. You can see that. Therefore, this can be written as e power r t into s naught integral minus infinity to minus d plus into 1 by root 2 pi e power minus s square by 2 ds. So substitute these two terms, I1 and I2, and then you have this. So we have P naught is equal to, what we have is e power minus RT into expectation of this. And the expectation of this is k times I1 minus I2. Therefore, you have e power minus RT into k times I1 minus I2, and that is equal to e power minus RT. K times I1 is this, P into minus D minus, and this is e power RT S naught into phi of minus D plus, right? Therefore, we have minus e power RT S naught into phi to minus D plus, and that gives me k e power minus RT phi of minus D minus minus S naught phi of minus D plus. And that is precisely what we wanted to derive as the explicit formula for Black-Scholes model, and this is called the Black-Scholes formula for European put option. So far we have established the Black-Scholes formula for European put option. Now we will establish the Black-Scholes formula for European call option. Recall that the put call parity relation is given by C naught. Remember, whenever we write the call option, we use the notation C, and that is equal to P naught, which is the price of the put option, plus S naught minus K into e power minus R capital T. Now we know what is P naught. It is given by this formula, and therefore C naught is equal to K e power R T phi of minus D minus S naught phi of minus D plus S naught minus K into e power minus RT. So we are just substituting the expression for P naught from the Black-Scholes formula for put option, and that can be rewritten as K e power minus RT into phi of minus D minus 1, which is coming from here, plus S naught into 1, that is this, minus phi minus D plus. Now note that phi of minus x is equal to 1 minus phi of x, and that if you use, you will get the required formula as C naught is equal to S naught into phi D plus minus K e power minus RT phi D minus. So remember, we know how this expression for phi is given, and D plus and D minus are given. Therefore, given S naught, K, R, and T, and also remember we have to have also sigma, which is the volatility. If all these are given to us, we can use this formula for call or the other one for put to find the price of the option. Say for instance, if K is equal to 25 and S naught is equal to 20, T is 3 months, and sigma is given by 24%, and the risk-free interest rate is given by 5% continuously compounded. So then if we want to find C naught, you have you can see that it is 20 into 0.04551, that is phi of this. How will you find? You first find d plus. In this case, d plus is given by minus 1.6954 and d minus is given by minus 1.8154, and then you can use the standard normal table to get this number. Phi of d plus minus 25 e to the power of minus 0.05 into 0.0351, that is again coming from the standard normal table for phi of minus 1.8154. So you should learn how to see the standard normal table and get this number, and that comes to be approximately equal to 0.0424. Please check the calculations carefully. So far, we have completed the derivation of the Black-Scholes model. Another nice feature of Black-Scholes model is that the Black-Scholes model can also be governed by a partial differential equation. So we will now see how to derive the Black-Scholes partial differential equation from the binomial model that we have studied so far. We assume that the parameters un, dn and r are of the form un is equal to e power sigma root delta tn and dn is equal to e power sigma minus sigma root delta tn, and as usual 1 plus rn is equal to e power r delta tn. This is what we will assume. If you recall, we had un and dn as something extra plus 1 alpha times delta tn and beta times delta tn we had in the previous section while deriving the Black-Scholes model. But if you recall, in the binomial model, for stocks, we have also taken this as an approximation to the general form of un and dn. So let's take this approximation, and this can be written using Taylor's expansion as 1 plus sigma root delta tn plus sigma square by 2 delta tn plus some terms which we will freeze and write as small o of delta tn. That is, the term which I am freezing here is going to 0 slightly faster than how delta tn goes to 0. And similarly, this can be written as 1 minus sigma root delta tn plus sigma square by 2 delta tn plus more terms which we will freeze as small o of delta tn. And similarly, this is 1 plus r delta tn plus the remaining terms. All this, as remember, you should always write this, otherwise it is mathematically not acceptable. We also take Pn star is equal to 1 plus Rn minus Dn divided by Un minus Dn. That you put all these expressions into this, you will finally get 1 by 2 plus 1 by 2 sigma into r minus sigma square by 2 root delta tn plus small o of delta tn, sorry, the root delta tn as n tends to infinity. So these are the basic parameters that are written in the Taylor expansion. Now let us recall from the basic binomial model, we have written the binomial pricing model as hn comma j, that is the price at the expiration is same as the payoff of st. Generally we write, if you recall, we write as any k comma j is equal to s naught u j dk minus j, right? This is how we generally represent this, price at the time tk is obtained by going upward j times and downward k minus j times, right? So the same notation if you use, I can simply write h as ht as h of s n comma j I can write. Okay, even here that is the notation where j is equal to 0, 1 up to n, and this is at the time level tn, that is capital T, and all the intermediate levels which are taken as tk. At that time the price is given by hk minus 1 comma j, and that is written in terms of hk, right? Because we are doing the backward induction method, and therefore they go, the previous time step depends on the time ahead of, and that is given by in terms of the expectation, that I'm just writing the expectation expression explicitly. You can compare it with our three step binomial model where we have written these formulas explicitly and shown. K equal to n minus 1, we are going backwards, and j will go from 0, 1 to k minus 1. Okay, you can see that. Just recall the derivation of the three step binomial model we did in the class, and the same generalized notation I am writing here. We can see that the pricing model here depends on tk, right? Because that's how k is coming here. It means the price h depends on tk and also sk, because every time step we are using this. Okay, and hkj plus 1 is a function of sk comma j plus 1, and similarly hkj is a function of skj, and therefore h is a function of tk and sk, right? The same we can also expect in the continuous model. H, the price, is going to depend on t comma s similarly, right? That's quite natural to expect, because we are getting the continuous model by taking n tending to infinity in these expressions. When these expressions are depending on the discrete time level and the discrete stock price, the continuous model will also depend on these two parameters, right? Where t belongs to 0 comma capital T and s is some real number which is positive, right? Generally we don't take s to be negative or 0, it's a stock price, therefore it has to be positive. And we will define the same thing with a different notation, that is h of t comma s. That is what we meant by this. Okay, you can imagine that t is taken as tk minus 1, okay, is equal to 1 by 1 plus rn. I'm just writing this expression in a different notation. H of, see here you have tk minus 1, here you have tk. So if I have t here, then it should be t plus one step higher, right? That is this term. And that is going to be, since you put j plus 1, it means from k minus 1, if you are going j plus 1 and j, it means this represents u and this represents d. Therefore, I will write this as sun, okay, and that happens with probability pn star plus this term htk. Again, it is t, because here t means tk minus 1. Therefore, tk means it is plus delta tn, and it is j, and that corresponds to s times dn, and 1 minus pn star. So what I did is I just wrote this binomial model in a notation which is convenient for us to use in the continuous time model. It is still a discrete model only. It is still a discrete model. return at any time, not necessarily at tk. Okay, it is written at any time. The price at present time is depending on the price at the future time with the time step as delta tn. That's all we are writing. Okay, the same thing we are writing in a different notation, and we use the following notation. This is just for the convenience. I will use this as hu and this as hd. That is the first term h I will use as hu, and the second term h I will use as hd, and then I write h of t comma s as 1 by 1 plus rn into hu of t comma s. Now I will write like this, pn star. It means this, okay, plus h. This is just a notational convenience I'm writing. 1 minus pn star. So I just wrote the discrete binomial model for any t in 0 comma capital T using these notations. Okay, that's all I did so far. I have not done anything more. Now I will define a discrete operator Jn. This is the operator acting on the price h. Okay, therefore this is something you can imagine as a function, which is the function is evaluated at the point t comma s, and that I will define as minus 1 plus rn into h of t comma s plus hu of t comma s pn star plus hd of t comma s into 1 minus pn star. So if I define a quantity like this, then what can I say about this quantity by comparing this previous expression? Yeah, you can see that this now implies that this expression jnh of t comma s is actually equal to 0, right? What I did, I just took this to this side and brought that entire thing to this side. Therefore, this side is equal to 0, and you have the expression same as what is written here. Therefore, your discrete operator, when it operates on the function h, it gives a function which is actually a zero function. It means it happens for all s and t. Now, what are we going to do with this operator j? Okay, let us take n tending to infinity with this operator j and see what happens.